All right, what's up, guys? So today we're going to be going over the word search problem on Leetcode. This is a medium level problem, and it's something that you're probably pretty likely to see in an interview for a big tech company. This will be something important. Yeah, with that being said, we just want to give you guys a little high level overview in terms of like pseudocode and the approach to the problem before we actually get into coding it. So I'm going to go ahead and let Japjot do that.
All right, so let's read through the problem statement. So we're given a 2D board and a word, and we want to find if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are those horizontally or vertically neighboring. The same letter cell may not be used more than once. Okay, so we're given this example here of a board, and some of the words that we're given examples with are these ones over here. So just looking at this and trying to find this word over here, the first thing that might come to your mind is, okay, let's see where an A is. Okay, this is the first A I spot. And then from this A, I can only go this way or this way because we can only go to horizontally and vertically neighboring cells. And so amongst these neighboring cells, I have an S and a B. And the letter I'm looking for next is a B. Okay, so I can go here. And then again, I repeat the same problem where I can only go to its adjacent neighbors. And then again, I see a C. And so I follow the same path and I can successfully construct this word. And so therefore I can say that this word is definitely within the grid. Okay, cool. So that makes sense for the first example. Let's read through the second example. So now we're looking for the word C, right? So let's look for an S. So the first S I see is over here. But this S, all of its neighbors, none of them are an E. Okay, so this S is not going to be containing the word I'm looking for. So another S, okay, yes, there is another S. There's another S over here. From here, I can either go up or I can go down or I can go left. But since the E's are only above and below, we'll look at each one of them, but we'll see that we have to go down this way, okay? And so this word is also within the graph. And then if I look for A, B, C, B, I see an A, I see a B, I see a C, but of C's neighbors, E, C, and B, I can't go back to B because I'm not allowed to use a word more than once. That was one of the rules that we were given. And so therefore I say that this word is not contained within the graph. So this already suggests that we want to use a DFS search problem. And the reason we want to use DFS is because we don't want to repeat words. Once we've used a word, we can't use it again, and it's sequential. So we can't look at multiple words at the same time. And so now let's maybe walk through what pseudocode for this problem might look like. So we're going to be given a grid, right? And so we need some sort of main function, which is going to take in this grid, and it's going to take in the word we're looking for. And we want to look through each of the vertices in our grid. And so I drew this picture up here basically to illustrate that if I took this grid, it's essentially, this is what the graph looks like. I draw a node at each one of the letters, and there's an edge connecting all of the adjacent letters. And once I have gone from one letter to the next, so remember with the example of A, B, C, this one over here, I got to A, B, C, but then I can't go back from C to B because I've already visited it. And that's one key distinction that always shows up whenever you're looking at a DFS problem on a graph, is that you don't want to repeat cells. And so that's one of the big things that should give you a hint for why we should use DFS in this problem. So back to the pseudocode that we were looking at. So basically we're given a graph. We want to go through all the vertices in the graph. And then for each of these vertices, we want to explore that vertex. And I'm being vague on purpose because when we look at the context of the problem, a lot of it will make more sense. But by explore, what I want explore to do is start from B and see if there's a path to reconstruct the word. And obviously, this suggests that if I look at vertex V, right? V is like either A or B, or it's one of these nodes, right? Vertex V is gonna have to be equal to the first index or the first character within the word. So that's one thing we're gonna keep in the back of our heads when we're actually implementing a solution. And then again, at a higher level, so I've written basically what my main function is gonna do. It's just gonna go through the entire matrix, and it's gonna try to see, starting from a particular node, can I construct the word? And then when I'm actually inside of the explore subroutine, I'm gonna do a couple of things, right? There's probably gonna be some initial checks I wanna do. For example, this condition we said over here, we wanna check that, is this actually true, right? Because if, where did I spell it? Okay, yeah, if this is not true, if V is not the first character in my word, then I know instantly that there's no point in continuing to traverse through this vertex because it doesn't even match the first letter. And so because of that, we could just return false immediately. And so that also reminds me, I forgot to mention that we're going to be returning whatever Explorer V does for us, because Explorer V is going to be telling us yes or no from a particular vertex. Can I construct the word I'm looking for? So in addition to this, there'll probably be a couple of other checks to make sure that I'm actually within bounds of the matrix. But that's essentially it. Because then after this, this is where, like, I guess the real like DFS part comes in, is that we're going to look at all of V's neighbors. So when I write V comma U, I'm basically saying from vertex V, there's going to be a bunch of edges going out, right? So from any specific vertex, say like this one, the edges are this one, and this one. So from each vertex, there's going to be some set of edges, and I want to go and try all of the different possible neighbors that I can reach, those neighbors being U, and I want to just repeat this process. I want to explore. And so this is essentially what distinguishes DFS from any other search. It's that you'll hear the term stack used very often, and we'll talk about it later to go more in depth, but this is the key distinguishing characteristic of DFS, where it's like I go to a different node and then I repeat the same exact procedure again in a recursive form of sorts. Okay, so now Aditya is going to jump in and go through the actual implementation of the problem.
All right, guys, so now let's take a look at how we can actually implement this kind of a problem. So like Jibjot said, the first thing we're going to want to do is actually go through each of the vertices within this graph. Graph meaning the grid, right? So in the context of the programming language, this grid is represented as a 2D array, or a 2D, like a matrix. So that instantly tells me that we're going to need some kind of a nested for loop, indexing with some I and j variables to represent each vertex. So the way we're going to do that is go through the board length and then go through each individual board index's length. So this is going to give us access to each vertex per se at the ijth index. So this is where we're going to need to kind of call our DFS helper function. And what I mean by that is over here, we're going to have to check a couple of things before we actually can return something. So the first thing we want to make sure of is that the cell we're currently at in the grid is equal to the first character of the word. This is how we're going to know that we want to actually start recursively calling our depth first search algorithm, because it wouldn't make sense to call it where the first letter, the first character doesn't even match, right? So that would indicate that our first check is going to be to get whatever is living at board ij and check if that's equal to the first character in word, right? The second thing we want to do is we actually want to make the recursive call to our depth first search algorithm, and we want to pass it the board, we want to give it the word, and we want to give it both the I and the jth index so that we can actually see and modify what's in the board at that position. So we're going to give it I, we're going to give it j, and then we need one more parameter. We actually need to pass through what index of the word we're currently searching for. So we're going to start from index 0, because that's where the word starts. We index by 0 in computer science. And if this condition holds, then we're just going to return true here. That is basically how we check to see that there's a valid path. And if we actually exit our nested for loops, that means that we've exhausted every vertex in this graph. We're just going to return false, because that means no valid paths were found. So now we actually need to actually write our helper function. So we're going to define this as a function that returns a Boolean, and we're going to call it DFS. As I said earlier, we're going to take in the original board. We're going to take the original word, the I index, the j index, and I'm going to call this index of or something like that. And remember, this represents the index that we're currently searching for in Word, like the character at index of in Word. So the first thing we need to do is we need to check for the exit case, right? We need to see if we've already found all of our letters in Word. And the way we can do this, if you think about it, in computer science, we index by 0, right? So the last valid index that we're going to be able to actually get a value from in Word is going to be word length minus 1. So if we actually surpass length minus 1, that means that we've successfully found all the characters in Word without breaking. And that means that we've actually already found all the characters in the sequential order. So that's going to return true. So the way we can write that is we can say if index of is greater than or equal to word length, then we return true. And then as Jibjot mentioned earlier, we're going to need some exit cases, or I call them break cases. We need to check that our I and j are actually still valid bounds, right? Because what if we accidentally try to check something that's off the board? Then we're going to get some kind of runtime error, and that's not going to be good. So the way we're going to do this is we're going to just basically check to see that I and j are still valid values within this grid. So if I is less than 0, it's negative, and you can't have a negative index. or if I is greater than or equal to the board length, or j is less than 0, or j is greater than or equal to board I of length. And then finally, we also need to check to make sure that whatever is at board ij is equal to whatever character we're looking for at index of, right? So if this stuff holds, or rather not equal to, if any of these fail, then there's no point of continuing on, so we just return false. So at this point in the function, we have already passed both of our break cases. So now we actually have to enter our recursive case. And the thing that marks DFS specifically is that we're going to mark certain vertices as visited. And the way that we can actually do that is by actually modifying what lives in that cell. And basically, before I actually do that, I want to store whatever's at board ij into a temporary character, because we're going to actually need to put that character back to where it originally was after we make our recursive calls, because the next time we want to reuse that vertex, if it's not reset properly, we won't be able to reuse it again for a valid path, and that's going to screw up the problem. So we've stored this in a temporary character, and now we actually want to set board ij to be something invalid, like a dash. And here's where we're actually going to make our recursive calls to our helper function. So now we're going to create this Boolean, and we're going to recursively call our DFS algorithm on the board, the word, because those are the original parameters. We're going to look at I plus 1, j, and index of plus 1. And I'm going to go ahead and write out all the cases, and I'll explain what they do in 1 second. Okay, so basically all we did here is we just made recursive calls to all the valid neighbors, right? So Jabjot mentioned that we want to check those u values, which represent the neighbors at a certain vertex v. So basically every valid path that we can reach from v. And if any of these return true, then we know that we're still heading towards a valid path. So that's good. And now down here, we actually want to reset board ij back to that temp variable that we stored earlier. And now from here, we just want to return whatever search gave us. So that's actually the whole algorithm right there. It kind of follows the structure of the pseudocode that we wrote, but if we actually go ahead and run this, make sure it compiles. And then we can go ahead and submit. So you'll notice it's actually faster than 98% of solutions, which is really good. I think that if you're able to produce this in any kind of interview, they'd be pretty satisfied. But it's your pretty standard depth first search kind of algorithm. And I've noticed with these kinds of problems, all you need to really do is adjust the cases you're looking for. In this case, we really just needed to check the index bounds and whether the character was valid and equal to what we were looking for. But yeah, that was pretty much the walkthrough of this problem. And, if you guys would like, we can definitely go through a more in-depth look into how the DFS actually works and the runtime analysis. But yeah, that was the problem.